Hello and welcome to the Daily Space. I am coming to you live from the International Astronomical Union meeting in Vienna, Austria. My name is Dr. Pamela. I don't know my name. My name is Dr. Pamela Gay, and today is August 21st, 2018. There's a whole lot going on and a whole lot of jet lag that is going to be part of this episode. But science doesn't care where you are. It doesn't care when you are. It's just going to keep doing its whole, science thing. So, for those of you who don't know what the International Astronomical Union meeting is, every 3 years we get the people in the astronomy community who are shaping our field either with the major discoveries or with the just as important educational work and, I hate to say this, administration and bureaucratic work that all goes on to move our profession forward, whether they are defining how we name things, such as with Pluto back in 2006, or how we plan as a planet to move our profession forward in the next 10 years. I'm here as the editor-in-chief of the International Astronomical Union newspaper, which is Keplerisch Nachrichten. I don't promise that I said that correctly, but we are Kepler's Notes, and we're working to bring you daily updates on everything that's going on here, as well as a bit of flavor of the city and flavor of the conference. So check all of that out at astronomy2018.cosmoquest.org. The Daily Space is part of CosmoQuest. CosmoQuest in general is a place where you can go to learn and do science. We are here on Twitch to help keep you informed, and if you click over to just cosmoquest.org, you can help us map out other worlds. But that's not why you're here right now, although if you have more screen real estate, feel free to go ahead and open up CosmoQuest in another window and map out the features observed by spacecraft on other worlds like the Moon and Mars. Guido, I hope you're really getting a good laugh at my German pronunciation. So we went with the German name for our newspaper to celebrate the German heritage here in Austria and Kepler's preference to live in German nations. But so to go with more news, to prevent my poor laptop from being as sad and beleaguered as it was yesterday, and I appreciate all of your patience yesterday as I struggled through the episode. Before I talk to you about what's going on here at IAU, I did want to bring you some really cool news highlights that are coming on. We have a great new release coming to us from Australian Northern University about the magnetic pole flipping of our own planet Earth. Now, our planet isn't going to reverse its orientation. I want to make this very clear. The North Pole geographically of our planet is still going to be pointed vaguely in the direction of the North Star as it slowly precesses in a circle over thousands of years. The South Pole is going to continue for a while to point at absolutely nothing in the vague area of the Southern Cross. But what will happen at some point we can't define is the north magnetic pole of our planet that your compass points at is going to decide it would rather, point out Antarctica. And so it's going to reverse and point through some penguins for a while. It's long been thought that this was the kind of process that could take millions of years, thousands of years. We didn't really know. We knew it flipped. We know it flips because of the records that we find in various stones. Stones from different periods had metallic substances within them align with the Earth's magnetic field, and they're found to align in different directions from different periods. As we look at the lava floor of different parts of the ocean, we can see in the lava generated at different periods magnetic fields pointing in different directions. Now, a new group of geophysicists got a new idea on how they can track these changes and maybe, time them with as close to a stopwatch as we can get with geophysics. What they did was they removed a stalactite, one of these carrot-shaped objects that hang from the roof of a cave. They're generally made from limestone and form as water percolates through the Earth's surface, erodes away the lime, and carries it down and, well, coats it onto this growing stalactite as it drips down towards the floor of some sort of subterranean cave, cavern, whatever you want to call it. Well, these stalactites in general grow like trees with rings marking the different seasons of the year, in this case, the wet seasons of the land where they're growing in. By removing one of these stalactites and looking at the rings and studying the magnetic fields and basically doing a whole lot of really careful science with a rock that used to hang on the top of a cave, well, they were able to figure out that in the past, these switches of the magnetic field have taken as little as 200 years. Now, during this period of magnetic field switching, the Earth's magnetic field will reduce by as much as 90% of what we currently have. And while that in itself isn't a problem, what is a problem is our magnetic field protects us from the sun's radiation. And what we're looking at is during that period, our Earth will be inundated with significantly more high energy particles from the sun and our, well, celestial surroundings. The last time this happened, our planet was a little bit less inhabited and a whole lot less technologically able to do anything. Nowadays, with that kind of high energy radiation and exposure to solar winds, well, a magnetic field reversal could cripple our technologies as it is today. This is one of those things that we really worry about because we don't know exactly what triggers a magnetic field flip. We don't know what warning signs it might have. We just know this could happen everywhere and reduce our entire planet's magnetic field, potentially that 90%. So these are the things that we worry about. But it is kind of nice to know that this reversal doesn't take the thousands of years, because that's civilization destroying. 200 years, hopefully, is something we can figure out how to get through. And here's to hoping that doesn't happen in our lifetimes. Now, in other stories we have coming to us today, the InSight launch, which we all watched a few months ago, well, it just passed its halfway mark on its way to Mars. So it continues on its way to have its own encounter with the red planet in November. And when that happens, we will bring it to you right here on CosmoQuest. Now, beyond that, we have a story that is one of the most amusing things I've seen all day, just because it turns out amateur astronomers should be allowed to name things, all the things. Amateurs need to name everything. It's long been recognized by aurora hunters that most solar aurora that you see in the extreme northern and southern latitudes light up our sky with these amazing green glows with sometimes curtains that include reds and yellows, but mostly green. It's mostly green. But occasionally, they'll capture these weird, bright streaks going across the sky. And I'm going to show this to you in the lamest way possible by pulling it up and showing you my browser screen. But this, I'm counting, will not destroy my connection. So, one moment while I open the image better. It has long been noticed by amateur astronomers that sometimes they see these crazy, bright spikes of radiation through the sky. And by radiation here, I just mean light. It's just light. And it was initially thought to be part of the solar aurora, but it didn't always appear. And so how was it that some aurora had these things, which the amateurs called Steve? This is our light ray, Steve. I really approve of this. So the amateurs named it Steve. And it's been getting explored. And they've come to the conclusion after prolonged study that Steve has absolutely nothing to do with aurora. It is this fabulous phenomena, and I'm trying to find what Steve stands for right now. Steve has nothing to do with aurora. So our Earth has a completely unexplained atmospheric phenomena. So Steve is a reference to the 2006 film Over the Hedge. When researchers presented data, and here I'm quoting from the press release from the American Geophysical Union. So to quote from the press release, when researchers presented data about the unusual lights at a 2016 scientific conference, a fellow space physicist proposed converting the name Steve, given by the amateurs, into the backronym STEVE, which stands for Strong Thermal Emission Velocity Enhancement. And the scientists adopted it. So go, you amateur astronomers, name all the things and then just tell us, and hopefully we'll adopt all of the names in the future. Now, I have one more story for today, and this is an explanation of one more of the resolutions that we're looking to vote on next week here at the 2-week-long International Astronomical Union meeting. Now, yesterday, I explained to you how these resolutions, they really govern all of how we do astronomy. So this meeting isn't all about what's latest and greatest in astronomy, although there's plenty of that going on. But there's also a whole lot of, wow, that's super important, but really boring going on. So in this particular situation, we have people working to define coordinate systems. And this doesn't sound like it should be something that's that difficult, but you have to agree on where 0 is. And you have to agree on how to calculate how to get from 0 to, 12, or 0 to 64,32.579. We have to know all the bits on the coordinate system, how to transform from one to another, and how to transform from the surface of our planet to low Earth orbit and beyond. And this particular resolution, which is titled 13th General Assembly Resolutions Presented to the 30th General Assembly Resolutions Presented to the 30th General Assembly Resolution B1 on Geocentric and International Terrestrial Reference Systems and Frames. And what this particular, it's just 1.5-page document. What this document does is it sets forth this idea that we have realized as we get better and better at measuring things that our current coordinate systems just aren't sufficient. Our current transformations to get from point A to point B on an orbital map, where what we're trying to figure out is exact locations at the altitude of a geocentric orbit. So this is the altitude above the surface of the Earth, where as you orbit, you are moving through space at the same rate that the Earth below is rotating. So as you orbit, the planet rotates. And if you're over the equator, you stay over the exact same point while you orbit. Now, if you happen to be north or south of the equator, when you get to that orbit, you're going to continue to drift south of the orbit, cross the equator, and come back north of the equator as you go around. But at the same time, you're just basically tracing a line up and down the Earth, north and south, as your orbit goes east to west at the same rate that the Earth rotates. Now, when you're up at geocentric orbits, you have to be able to do relativistic corrections to figure out where you're located, and you have to use very precise timing to figure out where you're located. And nowadays, we have GPS satellites, we have relativistic equations, and we have computers that can do extraordinarily complicated math on the fly from, your smartphone. And so in this resolution, what they're calling for is they want to adopt a new preferred scientific and technical set of transformations to be used at geocentric orbits and to be used in programming applications. This means that anyone who's writing software to describe what's going on spatially at that altitude needs to be using the transformations that are prescribed by this working group of the International Astronomical Union. They further go on to say that the IAU should engage together with other concerned organizations, such as the IUGG, this is a high-level geophysics community, I believe, and the International Association of Geodesy with the United Nations Global Geospatial Information Management System Subcommittee on Geodesy in order to promote the implementation of the UN GGIM roadmap for global geodesic reference frames. That was one heck of a wordy sentence. This is all legalese. We're voting on documents that bind our community together and say, this is how we're going to do it. So we're going to define exactly all the points on a map, if that map happens to be not at the surface of our planet, but instead at geocentric distances. This will become important for figuring out where spacecraft are, and, well, it's just always good to be able to discuss things with the same accuracy with which you can measure them. So those are the three things I wanted to bring up today. I apologize that our chat seems to have fallen over sideways on this recording. Again, I'm coming to you from Vienna, and some things happen. So I'm now going to take a look at the questions and see what I can do to answer things. So I see that Henny's Vorverb is asking, so would this have to be implemented by rocket companies? Yes. So the idea is that this particular set of coordinate systems, any application, whether it be how you calculate the orbits of your spacecraft or just how you track things in your desktop software for tracking satellites, all these applications should be using these new reference frames. Let's see what else we have in there. Thank you for the person who said that our newspaper is pretty. I'm the person who designed it, and it was done very last minute, so I appreciate that. Everything should be named George. This is kind of how I live my life. I name everything pretty much George or Fred unless it's a pet. So I'm scrolling through looking for more questions. I'm not seeing any. So do you guys have any more questions that you want me to answer? Go ahead and just at me in the chat. So Magnus Themer, I'm not sure if I said that right, I hope I did, asks, do we know if the other planets' magnetic fields, the ones that have them, also periodically reverse? Also, year-long fan. Thank you so much. I've only been here for about a year, so you've been here since the beginning. That's awesome. So we don't know. We just don't. We get catches of bits of entrapped magnetic field on the moon from, well, we're not entirely sure. Mars probably had a magnetic field in the past, and hopefully the more we study, the more we'll understand that. But Jupiter's really the place in our solar system where we're able to study other magnetic fields. And at least during the lifetime of the Cassini probe, it didn't reverse. And I don't know if we'd have had any way to know, other than having it happen while Cassini was there. I don't think we'd have any other way to know about its reversal. Now, I could be wrong. This is me thinking through as a scientist, and I just don't know. So something just made good noises. Let's get some stompy feet in the chat for SB Average Joe, who has given us a follow. So welcome to the group, SB. Welcome from Miami. Without an iron core, what generates Jupiter's magnetic fields? So it turns out you don't actually have to have a metallic core to have a magnetic field. In fact, our sun sure doesn't have a magnetic core. What you need is charged particles. Anytime you have a charged particle, whether it be a carbon atom that's missing a couple of electrons, or whether it be just a straight out electron by itself moving in a circle, that circular motion can generate electricity. Not electricity, can generate a magnetic field. A magnetic field can generate electricity. These are how the electro and magnetic field forces work together. So that 900th follower, That's amazing. Amazing. Thank you for the 900th follow. I now see why everyone is so excited. And thank you, Fenrig, for gifting the sub. So, charged particles moving in a circle generate a magnetic field. Our planet has a super hot inner magnetodynamo, this layer of charged particles inside the planet. And as those charged particles go round and round, apparently not exactly perpendicular to our rotational axis, then we sorry, I'm getting distracted by the chat. Anytime we have charged particles moving in a circle, which we have inside of our planet, you get a magnetic field. So the key is having a liquid core or a gaseous or a plasma core. Gas doesn't really work, or a plasma core. By having that stuff in motion inside your world, that generates a magnetic field. Venus isn't that much smaller than us. In fact, they might be. Venus is similar size to us. I'm very jet lagged and not remembering exact numbers. Venus is very similar in size to us, but it has completely different geography. And it's not rotating the way we are. And this has led to it just not having a magnetic field the way we do. So Hanny is asking, is there any electricity flowing through the planet because of the magnetic field? Well, by definition, anytime, and my lighting has gotten way the heck too bright as the sun has set. Sorry about that. I'm beginning to look like a crazed, overly lit person. There, that's a little bit better. Anytime you have charged anything, you can refer to it as a flow of charge, which is the same thing as electricity. Now, electricity in our wires, that's just a flow of electrons, just electrons getting along, doing their thing. We have a flow of charge, not necessarily electrons inside of our planet, and that's going to generate electric and magnetic fields all together. It's all entwined, but it's definitely not something that's going to power the way too many lights I have turned on in here. You can always name a horse George. I actually knew a very nice horse named George. He was a big bay thoroughbred. I approve of horses named George. I had a horse named Ben. Do we have other more scientific questions? And my lighting is just terrible now that the sun went down there. That's a bit better. If there are no more questions, I'm going to tell you I will be back tomorrow. Same back time, same back channel. Now, the daily space right now is running an hour later than normal. It will be doing this for the whole 2 weeks that I'm here in Vienna. This allows me to finish wrapping up the day's newspaper before I take on the day's daily space. So it's kind of all news for the next 2 weeks. Thank you so much for the 50 bits. I'm not sure that'll quite get dinner and wine, but it will sure allow me to upgrade the beer I'm going to get. So thank you so much. Welcome to 1 hour later. We will be doing the Astro 101 courses on Wednesday and Friday at the normal daily space time to try and make things a little bit easier on your day. I will be here on Thursday, and directly following the daily space, we are going to be doing learning space, and our special guest is Amy Davis Roth. She is a professional artist who brings science into everything she does. And she's been a huge inspiration to me, and I hope she'll be a huge inspiration to you. Now, I'm not seeing any more questions out there. And if there aren't, I'm going to get back to work because that's what I do. But I'm probably going to order myself a little bit of room service. So thank you all for coming. CosmoQuest is a collaboration of multiple institutions. We are run out of the Astronomical Society of the Pacific, and here on Twitch you will see Dr. Matt coming to us from the Planetary Science Institute, as well as Annie on Science Sundays, showing us how we make art out of astronomy for planetarium shows. She comes to us from Youngstown State University. Check out everything we do at CosmoQuest.org. And please make all the efforts I'm doing editing the newspaper for IAU worthwhile and go check out astronomy2018.cosmoquest.org and share it with your friends. Get the news out. And if you've ever wondered exactly what is it astronomers do, this newspaper will help you find out. So thanks for coming, and wherever you are in the world, have a fabulous morning, evening, or afternoon, and get outside and look up. Bye-bye, everyone.